Dr. Pratyush. I'm adding him.
Okay. Bye. Mangal, see you soon. Okay. Uh,
Okay. Professor, can you try sharing your screen and checking whether it works?
okay. 1 minute. How do I share? And who should I share screen to? Or I share window or screen? Which one I should share?
Screen is better.
Okay. I will share screen too. And I say share. Come on, share.
Yes,
It's an empty screen. Yeah, you can take it there. And please go to the full presentation mode.
Yeah.
Okay. Okay, I think then we can start, right?
Can you hear me correctly?
Yes, we can hear you. Can you hear us?
Yeah.
Okay, so I'm Ashish Datta, and thank you for agreeing to spare your time to make a presentation.
Thank you, Ashish. Thank you for the invitation.
So welcome back to the session for plenary speakers. We have our last speaker for today, who is Professor Pratyush P. Menon, who is an associate professor in the College of Engineering, University of Exeter in the UK. And he is also the deputy director of the Center for Future Clean Mobility. So Dr. Menon will speak to us on autonomous oceanographic sampling today. So welcome, Professor Menon, and the floor is all yours.
Thank you, Ashish, and thank you, Mangal, for the invitation. And I'll share some of my experiences in the field of autonomous oceanographic sampling. So So I thought I will just give you a rough idea of where I am located. So I am at Exeter. So Exeter is here. So it's about 200 miles southwest of London. And it's very pleasant city, a small place, and close to the nice beach and everything, and near to Dartmoor. So that's the sort of a overview of the place where we are, some of the buildings, and we do have multiple campuses in Devon. So we have 3 campuses, one including in Cornwall here. So that's basically Exeter. I would like to invite whoever would like to visit us whenever we can. It will be a great opportunity to collaborate and work together in future. So I then go to next, an acknowledgement to all the colleagues, the team members of the project. So that's my PhD student Chiara and postdocs Shannon and Gian Mario. Together with Peter and Chris, we work together as a team in this project. So thanks to the funders, these projects are funded by NERC and Innovate UK. So 2 projects combining autonomous observations and models for predicting and understanding shelf seas and adaptive autonomous ocean sampling networks. So the first one, the combining autonomous observation, we are just in the progress of the sea trials and just finished and starting to do analysis of the data, everything. I have kept some results of it, but it's not published anywhere because Mangal had been saying me to present something new as well. So that's what there. And still some more, the works, I would like to say quite a lot thanks to many different organizations we work together. So in the project we worked with mostly the sort of National Oceanography Center, NOC, Southampton, Met Office, Exeter, so who we make use of the data from Met Office to do quite a lot of planning and analysis. Then PML, Plymouth Marine Laboratory, who basically lead the project, and we are part of it. So it's a very large project, and several partners are there, and we are just so our part is mainly in the area of autonomous systems, like how the autonomy can be inbuilt to make the oceanographic applications nicer and efficient. So just a disclaimer. So it's a picture, Daniel in the lion's den. So I am at the moment sort of Daniel, and I'm not an oceanographer. So there may be some questions maybe coming from the oceanography side. I will try to answer them from some level of approximate, some functions or bounds or etc. So yeah, that's a disclaimer I want to make. And the outline of talk, I will just give you an idea of different applications in the oceanography area. That's why I put the disclaimer at first. Then general philosophy here in terms of autonomy in the oceanography. And so two type of works from the two projects I have kept. One is just autonomous behaviors. It's a surface vehicle mainly, but they are extendable to other vehicles, which I will show you. And then information enabled planning using gliders. That's what currently we are working on in this project. And what further in our shelf and where we are heading to in coming couple of years, at least. Yeah, that's the sort of outline of my talk. I believe I'm audible correctly, right? Hello?
Yes, you are.
Okay, thanks. So there are several oceanography applications, and they are often linked with understanding the biodiversity of the ocean and the climate change and aquaculture, etc. One of the key issues is something called tidal front. So this is same photo of what I have been showing Exeter, and this is the tip of the Exeter Cornwall region. And here longitude and latitude, and the color just explain the sort of how the sea surface temperature is. Okay. And the tidal fronts has some very specific connection to the sort of mixing, and it depends on the temperature, how the temperature just of the ocean just change. And here on our right side here, what you are seeing is with respect to depth, how the temperature change, and here you can see in the yellow sort of a front, and there what the mixing happens between the sort of or stratification and just about the mixing. And that specific temperature region is of the interest. So as you can see, it's not at a constant depth, it just keeps changing, and like so these are the sort of contours of a specific temperature. And that is where most of the oceanographic measurements are to study the details of chlorophyll or presence of protein, or how the light, or what is the level of oxygen, what is the sort of temperature, what sort of planktons are there, etc., need to be studied at those sort of regions, because that tells a lot about their change and everything. So next is similarly like the sort of short-lived vertical circulation. So at terms, the sort of heat exchange creates some specific change in the sort of sub-mesoscale dynamics. That's about spatial scales of 1 to 100 kilometers and specific temporal scales, because these are spatio-temporal activities. So if you want to model this, these are like a partial differential equations, and we need to simulate it over quite large region and for large time. So the specific dynamics is for days to months. So it's very expensive to do any sort of simulation and understand what is going to happen as well in terms of this sort of heat exchange and heat budget, and how the climate change affect the health of the plankton, health of the sea, health of the shelf sea. This is very much related here, and why we are interested in this sort of applications. Here you can see this is the sort of phytoplankton, and that's this picture shows the food web, so in the marine environment, and this phytoplankton becomes the key. Like in future, humankind will be struggling for the water source, where the water, and that's what going to be the challenge in future. So similarly, for the marine lives, the presence of phytoplankton is very, very important, because that's the primary sort of element which just feed, and the sort of like a nice graph goes on. So the appearance of this algae, and some of them could also be dangerous, and there are some sort of issues there as well. So it's just show a picture here around the Cornwall in this region, how this is just a satellite measurements which PML has, and it shows how over the period the sort of the algae bloom changes, and this sort of red color is more tricky. So like this is something which we need to really study. So now we looked at sort of a temperature issues in sea, then like the sort of temperature and oxygen and the presence of chlorophyll. These are all interlinked, and we need to study about it. And when I mention about it, it's this sort of problem what we have been doing in the Plymouth or Cornwall side is equally present in the Indian context as well, because if you see, there are some published work where the appearance of algae bloom in Bay of Bengal, and they do. So this is the sort of region where they have looked two regions so close. So this square box, and how things change over a period of time, and another one here. So, and they show this so this is the box A and this is the box B, and how the chlorophyll change over the years. And this is a periodic event as well, because typically associated with the sort of temperature increase and the sort of monsoon and all that links there. So to have efficient mechanism to monitor and all, rather than at the time we sit on a boat and or a ship and just go with the bucket and just dip in the water and see what happens, it's far better to sort of consider the use of autonomous vessels, which can be deployed over the years and etc. in a consistent manner and improve on that. So that's what we are doing here. That's what the role of Exeter with all the NOC, Metofis, and Plymouth Marine Laboratories and CFAS. So similar sort of agencies are in India as well. I have previously worked with people at NOC, not NOC, National Oceanography Center, Goa. So we were doing marine robotics course in perhaps a few years back with Antonio Pascal and those team. So it was a nice time. So what we are doing is we are building a framework along with this deployment facility at National Oceanography Center at Southampton for the use for upcoming years and years and sort of. So there is lot of formal ways to do this. So there is a lot of research, low technology, TRL level, readiness level, lot of research work there. But at the same time, there is quite a lot of practical, higher technology readiness level aspects and a lot of software development to link with different infrastructure, different standards, and all that issues are also there. So now some resemblance here. We all know it's just a MATLAB plot of a peak function. So if you look here also there is colors, here also there are contours. So basically, many of these problems, what this oceanography or like biodiversity assessment people wants to figure out, we can nicely translate it into a language which we know, comfortable zone of parameters x, and y, saying location, could be lat long, and some cost j. J is, it could be the presence of chlorophyll, it could be the sort of a probability of oxygen, etc. So it will have certain maximum and certain contours. So that's what, so here in the blue, you see the maximum. Here the orange color is what I'm indicating with the sort of a contour. So we transform the problem into seeking the maximum or hotspot source, or just looking at boundary seeking or boundary tracking, etc. problems. So that's a sort of a resemblance in our community, in control community at least. So the philosophy, okay. How many of you know? I'm not sure. Maybe all of you know this vehicles, right? So it's my daughter insisted that I should keep this diagram in my talk, so I just kept it. These are different. It's a nice cartoon. It's the inspiration for many of our works as well. So it's octonauts in BBC CBBS. I don't know whether you have seen, but it's worth watching. Very comforting, very nice. So there are different types of vehicles. So GUP-B, GUP-S, GUP-X, very advanced one, bio-inspired, etc. And for different applications, going at different depths for different like that. So similarly, now leaving apart the cartoons there, let's now move to what actual vehicles are there in our assets at NOC at least, or various agencies put together. We have several platforms available widely and being used for multiple purposes. And they can be used for different spatial as well as temporal periods. And these observations range from large-scale processes to small-scale variations in different temperature, oxygen, pH, etc., TPH, all that. What I have to mention here is true autonomy is still not achieved with these sort of systems. Often they say these are autonomous vehicles, but what this autonomy means to the people there, it's basically a vehicle which they send, not a ship, with some sensor, and it collect the information, it come back, we just download the data, look at it. This is what they conventionally doing even now. So that's where we are trying to bring on some level of intelligence embedded into it from the perspective of control and optimization side. So that's the idea. So sort of either decisions are made for the vehicle on board or from the shore and communicated it through satellite, because most of them works through the Iridium communication or like we could do through this mooring buoys and like where there are sort of a mechanism to communicate. So this is the sort of like a wave glider powered by the sort of wave energy and the PV energy, etc. Here, this is the glider, the Slocum glider, named after Joshua Slocum, who alone traveled around the world and is buoyancy driven. So that has more endurance and it doesn't, yeah, it's suitable for longer, whereas this is the sort of vehicle which we work with as well, which is an unmanned underwater vehicle. It's a sort of eco-sub made by Planet Ocean. It can go, there are different varieties available, which can go up to 250 meter depth to up to 3,000 meter, about 3,000 or 2,400 meter depth. That number is slightly, I'm not now remembering precisely, but it's about, one is about lower depth level, about 250, and the other is about 3,000 meter deep it can go. So they typically just go through a pre-planned sampling designs, sort of lawnmower, and this is, so you could make a connection with the sort of unmanned aerial vehicle situation as well, because I'll just get to that now. But yeah, these are the sort of different sampling designs which oceanographers make use of for different applications. So there are different problems. One may be sort of like we want to cover the entire region. Sometime then, like, yeah, this sort of with one vehicle lawnmower may be very good, easy. But certain cases, like what I have been showing you earlier in some 3 cases at least, they would like to have more adaptive and autonomous sampling, because that's what happens. They come, they do the survey, or they do the deployment for about 3 months, and after the 3 months, so in the middle, they dump all the data through Iridium in their computer and analyze and see, okay, we didn't get the data, just missed it. We missed that bloom. It was there. You could see a little bit in the satellite, but we missed it. By then it just, because these are dynamically evolving, so that's over the spatial and temporal field. So that's something we need to remember. So that's where, if we convert the actual practical problem into the sort of seek the source or find the boundary, we can embed intelligence into the vehicle which we make use of. And yeah, so embed intelligence into the vehicle so that it can just track the boundary or get the source. So how we do, so what I say about the autonomous behavior is some sort of assumptions or some clarity to have. It's without any piloting intervention, and it decides the guidance command. So we are not doing at a low level controller often, because we work with third-party vehicles, so it has its own insurance and everything. We don't do on a tank. So we like to work on the guidance level, because it is a planning level. We command it and increase the command. So there is a sort of concept of front seat, back seat driving as well. So we are okay with that, but we may not change the original controller on board. We will keep the original controller of, say, if it is the glider, the Teledyne controller, it will be there, as well as if it is the Boeing waveglide. We will keep that controller, but we just work on the guidance level in terms of where it should steer, where it should go in terms of waypoint, heading hold, etc., like that. So that's the idea. Then the decisions are made based on, so where to go is decided based on instantaneous measurement of quantity of interest. So this quantity could be whichever. So accordingly, there should be a sensor placed. So we write the generic codes and generic stuff so that a different sensor can be put on, and all this are done using the sort of up-to-date standards. And we assume that sensor is capable of offering the right data at right rate and format. There is flexibility for the frames, how many frames we want, and there will be sort of, I will show you some results on how the quality change and everything. So let's get to some maths behind it. So like I said, this diagram, all the aerospace people will very easily recognize it's a UAV quad or everything. So it's the sort of kinematics, and V cos theta V sin. So that's the set of equations, kind of basic kinematic equations. So here what we look is the sort of a contour and a maximum is shown. So we assume that, so this is for, in practical, you won't see any sort of isolated maximum, etc. like that. But this is given to clarify how we typically look at it. This is, if you tell this immediately, the oceanographers will just wake up and just go. But for our convenience, or like our satisfaction, let me put it that way, for the proof of convergence of algorithms and etc., these are good. Then we can show some variations to that. If it is not isolated maximum, what will happen and all that. So that's what I'm doing. So the boundary is then a smooth, simple contour defined as this compact level set. So here as shown. Okay. And again, this is at the moment as shown as a static, but this could be a dynamic. I'll just show you. So this is the sort of how we will just show the proposed steering law. So this box here will be the sort of vehicle, and here we introduce a additional set of elements. So this is the sort of sensor just giving the measurement, and here this is the sort of a guidance block sitting to provide the steering in terms of waypoint or a heading. And I will explain what we are doing immediately. And this at the moment presented in a local scope, because all this no global proofs, it's all local. So we make use of a concept very popular in control, which is the so-called sliding variable. So if this sliding variable is not very sure, we define a specific surface in terms of that quantity of interest. So this gamma can be sort of chlorophyll or oxygen, temperature, whatever, and that we want to have some sort of reference. So if my interest is, because science applications, they know I want to monitor in the region of between, say, in a range of 16 degrees or like 15 to 16. So there is some sort of a variation range which they would like to. So we can nicely write that. And this sliding variable, so what we do is we define this as sort of a surface in an imaginary space, or like a space, and we try to steer the movement of the sort of a kinematics and thus that dynamics there with this measurement, such that the forcing just makes sure it stay in that specific defined surface for all the time. So that's what we are writing here as a sliding motion along this sort of a surface. So this is equal to 0. The gamma is instantaneous. Then it becomes the desired. Then it is this surface is. So we have a plane. So what we try to do here now is, this is a standard approach in the sliding mode community. We differentiate the sliding variable, obtain the sort of equation. So here, this term is basically the magnitude of spatial gradient. But what happens is the spatial gradient is not available in practice, and we need to. So this is the real issue, because we have instantaneous measurement, but we don't have instantaneous velocity of that measurement. So what we do is we take one more differentiation of that signal, and that's sigma dot, and obtain this. So if you see, because if you just go back here in sigma dot equation, there is no presence of the control input. We don't have any sort of a forcing function there. So we need to do a one more differentiation, we obtain that. And then if you write this if you look carefully, this terms v is the velocity, the sort of the spatial gradient, theta dot is the sort of so just one quick go back. So theta is this angle with respect to velocity, and this is the angle of this sort of condor. So if theta becomes phi, what happens is this vehicle just aligns to the condor in that direction and it moves. So this is what we try to attain. And when you write this, sigma dot becomes the sort of a term that is uncertain time varying drift term plus a time varying gain term of the control input and a matched uncertainty, because again, how this phi dot is the rate of change of the sort of contour. So the curvature, we don't know that really, because yeah, we are just jumping. So like that's what happens. So, but this is sort of a relative degree 2 problem. So what we want in terms of forcing, so now if we design the control input, we want to make sure that sigma dot and sigma go to 0 at to maintain the sort of sliding, and everything works fine. So this is a very generic form, so introduced quite long back originally by Bartolini, and there is and Antonella. They have worked a lot in this sort of structure, and this classic structure is there. So what we do, without any sort of modifications, we have just used that suboptimal sliding algorithm as the steering law, where R1 and R2 as some positive terms, and it enforces sliding infinite time. That implies the tracking happens perfectly. So what you might not have noticed very quickly is I immediately use this gamma ref. It's though t time dependent, I have just made as a static. So there are no derivative term coming here, and also this is because the analysis we do as a split analysis. So what then we do is the dynamic case. What we do is if you have a gamma dot, and if we just if we put this sort of a logic, what happens is this argument here holds exactly right. So I'm not going into those sort of details because that requires quite a lot of derivation and passage, and the time will not be sufficient. But yes, you can have the time variations, and still it will just align to the existing generic form as you have seen earlier. And this is in the case of boundary. And if you are just putting, instead of the boundary, if you are trying to find a maximum, you just need to have a sort of a small positive scalar chosen, this delta, and as long as the sort of sliding is within that sort of bounds, you keep a scalar gain k, and it depends on the gain. The sign of the gain will depend on which side of the contour, whether you are climbing the sort of the gradient or just descending the gradient. So because yeah, a contour just separates to the two regions. So one is like where the intensity increases, and the other side is it decreases. So just we have done speed adaptation. So the vehicle follows the contour line, theta is equal to phi, and the estimation of the curvature also can be done online. So what we do is we just introduce some sort of adaptive elements into that. So the vehicle can accelerate if the sort of a curvature is not sharp. If it is a sort of if the contour curvature increase, the vehicle just reduces speed automatically. And if it is just the contour curvature is flat, we just increase. We have done that work as well. so yeah, this is what Lewis Hamilton would do when you just watch the sort of Grand Prix, the motor race along the tight contours. The speed just reduces a little bit. This sort of work is brought into in the speed regulation loop. So that is also present. So we could achieve quite good results. So just quickly some numerical results on that, like without any speed adaptation, keeping a speed of 10, we get this level of error. This is purposefully done. If you reduce the speed a little bit, say about 6, if I recall, this boundary tracking is far improved. Okay. So now what happens is if we switch on the speed adaptation, the speed varies as the sort of curvature changes and these sort of corners, and you can see here the improved tracking is obtained. So here the velocity just varies as well between 10 and about 4 as well. So when there is contour is tight, it reduces the speed. So these sort of algorithms are written in the robotic operating system and uploaded to do the sort of testing. So let's go to the testing details. So trial planning, we did sort of, we worked on very staged planning with starting with virtual trial, then the hardware simulator, hardware software interface. So some of the elements we kept. So sort of what I would say is the success of trial is in terms of going step by step and identifying we have addressed various individual elements correctly. So in virtual trial you could ensure the algorithm functions very well, and you can use the realistic synthetic data available from the other agencies to make sure your algorithm still works in that. Then we can just introduce the other sort of hardware elements such as the communication and the sort of the reaction times for the vehicle, etc. So that's what we do in simulator trial, hardware simulator trial. Then we go and we just put in the sort of area where it is secluded. So this is, we did the test in SAMS up in Scotland. So this is the area Oban. Oban is a place in Scotland, and a well-known whiskey comes from there. So here we put, and in this bay we test first because that's an area secluded sufficiently without much wind and quite a lot of good control and without much other interacting vessels. So we do some Wi-Fi range in water experiments, we tune, we calibrate the gains, because yeah, we have two gains, R1 and R2, and then a K, which is the sort of the adaptive gain and all, but we need a little bit of tuning when we put it in the water and try that. So that's what we do. And then we carry out the test in actual sea, which is the Ardmurnish Bay here, where there will be quite a lot of disturbances from waves and all. So here this water is still almost. And then we want to test it beyond Wi-Fi and commanding it through either through satellite or on board. But this part I have not done because of the time and lack of money, because iridium is very expensive. So we implemented all this sort of methodology on this vehicle owned by NOC, built by ASV, which is the so-called Sea Enduro vehicle. And we put it all as an embedded system and created our sort of guidance algorithm in this UOE node, so University of Exeter node. And then the sort of depth sensor was put on this sort of heel here. So, and we design the guidance part and communicate with the ASV pilot. So this is the virtual pilot laptop, which communicate with the sort of commanding for the ASV. So yeah, quite a lot of interaction was done with the company to get it all in place, and step-by-step testing. So some virtual trials, we made use of the data from some specific depth and bathymetry. So here, we couldn't do first as a, okay, I didn't mention what the exact experiment we were doing. So the idea was follow a specific contour. So the contours of specific depth, we want to make the vehicle go through a specific contour. So as you can see here, there are different depth contours. So one of the depth contours we wanted to follow. That's what we were doing. So here, this is the point where we command from. So this is where we locate with all that what I have shown you with this UE node and the computer and everything. And here we just send it and communicate it. And there is the sort of Iridium connection for monitoring purpose as well. And some video here, hopefully it works.
Laser pointer.
Yeah, I think it is now working. So yeah, this is this is monitored from the NOC end at Southampton. So we are in Scotland. We are doing the testing. So this courtesy for this video is NOC. So they were monitoring how the vehicle is called Thomas, and this we are traversing a 20-meter contour. Or no, I think it's a 20-meter contour. So we were traversing that specific contour. So this contour information is a priori obtained from the ADCP. So from using the ADCP, we know exact contour. There is a mapping, and this information is available through the hydrographic office. So now, but there is some changes in between. The reason is because there is the sort of waves and the tide. So there will be some sort of fluctuations and variations. What we actually missed here is just before the sort of trial, the ADCP we just spoiled. So the ADCP equipped on the vehicle was just hit on somewhere. So it wasn't working. So we didn't get instantaneous data to verify further from the ADCP. But what we did was we just checked with the sort of hydrography office what the level of oceanic waves and what the depth, then make the comparison. So this was part of a competition, and which there was the NOC competition on doing this experiment, and we won this work, and it was well appreciated by DSTL. So there were many people with medals and everybody just standing around and watching this experiment. It was tricky and giving a lot of pressure. I became more old at that time. So yeah. So that's the story of the surface vehicle sea trial. Some are how the tracking error. So there were about some points where the sort of gradients were very high. So this is without any speed adaptation, because they didn't allow us to do the speed adaptation on the vehicle really, because they told it is more risky. So first let's do the testing without any adaptation. That was the idea. So there is a little bit of error here in terms of tracking the contour by 2 meters, 4 meters, up to 4 meters. And here we lose it because the Wi-Fi, which is lost, the loss of Wi-Fi is the 0 in the red curve. So then we did more tests, and they were tracking 32-meter contour at higher speed. We wanted to assess how, if we increase the speed, how much variations will happen. Without any Wi-Fi, so we came closer and good Wi-Fi range. So about here, the Wi-Fi limit was. So we managed to do sort of 32 meter, and maximum was about 6 meter variations. But these are quite good for the oceanography one. But like I showed in other numerical and data, it is possible to have more detailed, more sharper one. But in oceanography, up to 5 meter and all, not a big problem. In certain ones, there are issues. So it depends on the tweaking of the gains need to be done accordingly to the specific applications which you are interested. So now the second part, the information enabled sampling. So the idea is we want to monitor the algae bloom in. So here this is Plymouth is very close to Exeter, 70 miles south further, and from Plymouth, PML, Plymouth Marine Laboratory here, and this is where L4 is a location, and this Eddystone is a lighthouse, very famous one. And so we do the testing in this area. So that's quite long away in the sea, and we want to monitor the sort of how the algae and the probability of occurrence of algae maximum. And we did the sort of using the data set, we did the sort of proof of concept of different possibilities of a specific contour to be followed if required. This is the sort of red, and this is the band within it, which the glider should just sample and obtain the data. And this is sort of like, this is not glider, this is the sort of eco-sub vehicle, the underwater unmanned vessel, which need to track the sort of a specific contour at a specific depth. But this will be just dynamic. So there will be occurrences of this completely getting lost, as you see. But as soon as because if it is, there are certain issues I haven't discussed in the theory, because if you are far away from the sliding surface, you could just have issues. Or like if you have no measurement at all, there could be issue. That's why I was saying about local result, and under assumptions, you get quite a tight set and everything. I mean, theoretically we can show, but in practical cases, sometimes it will get lost. But what is most important is, if there is a bit of presence coming around the vehicle, it should immediately tap on and get it. So yeah, this is the idea. And these two vehicles, but due to all the sort of COVID situation and everything, we weren't able to just do both of them. We were just focusing only on the glider. We haven't deployed the eco-sub. We just made use of the gliders. So how we do the glider? So the glider, there is a sort of two things: surfacing profile and yo-yo profile. What is the key issue here is, okay, the kinematics, there is this kinematics, but the glider has a very specific geometric constraints in terms of its movement, because these are buoyancy driven, and hence it just create lot of trouble, because on top of the sort of normal sort of kinematic constraints, it also has a sort of specific geometric constraints, because it can just go set of like a dives and the climb. So that's so it dive and then it climb, and that's the yo-yo profile, and it has to follow that. And these are sort of mission requirements and constraints, because like I showed you earlier diagram, just making very adaptive changes, NOC people, they didn't wanted to do that because they were saying it is more risky. So they wanted just doing a very fixed 6 hours path plans, dive, climb, and about 20 minutes it comes up on the surface and give us all the data. So when it goes down, it is all dead reckoning. So we just show some of this captured exactly in the code here. And these depths, so we are interested in the region of 5 meters below the surface of the sea and 50 meters below the surface of sea. Between this band region, 5 meters to 50 meters below, it should just keep gliding. And what we can provide is the sort of waypoint only. They wanted to keep the 26 glide angle constant. They didn't want to change it right now. But we have showed them what the advantage you get by just adjusting this, as bringing that as also as a variable to do some bit of optimization. So then there are sort of forbidden regions in the optimization, because there is a lot of marine traffic goes on. It's by side of the shipping and the Royal Navy practice zone. So if they see something moving in the radar, they may shoot it off. So there are issues. Then the idea is the navigation should be such that it maximizes the information gain. And I will explain what is the information gain. And validation of occurrences of algae bloom events, and assimilate the data towards reduction of uncertainty in forecasting where the algae bloom is going to be. That's the whole idea. So we come up with an iterative probabilistic learning approach. We have a lot of forecast information from metaphase. They have the supercomputer just giving what the probability of algae going to be for next 5 days and next 2 weeks. So all that sort of preliminary information there, and from the satellite and everything. So, but these information, as you see, as you know, these are sort of like depends on the boundary value for the PDE. So you can think of this autonomy is sort of, you have a 2-point boundary value problem for the PDE, and you just look at the right boundary value conditions just instantaneously provided, because the boundary values keep moving. So the initial condition just keep moving, and accordingly, so there are sort of quite a lot of similarities to the sort of adaptive simulations and mesh generation. Then also to the sort of MPC model, predictive control ideas, etc. But we can't make use of any of those data for instantaneous use, or even for planning 6 to 12 hours, because they are very, very expensive to run. It takes huge amount of time. So what we do is we create a probabilistic short-term forecast model based on the Gaussian process ideas, and then make use of that to do the path plan. And that path plan is sent to the sort of gliders through the command center, because they validate. And when we create the path plan, we just account all the sort of different constraints, and we put this command, and then we check what it happens, and it just keep on going iteratively for months. And what the idea is, over the time, once it starts and weeks after week, it should improve. So there should be a learning in the way of how the prediction is happening, and there should be then like very reduction of uncertainty in prediction. So that's the idea. So what sort of a short-term forecast model based in statistical model? So it's like a mean, prior mean, and the kernel is defined. So based on the available data, we just say a global trend. This is the mean function, mean regressor, and then like a kernel which just show about the local variations or fluctuations. So these are sort of covariance information, and we put specific. It's just one thing I have shown is the squared exponential, but this could be like a Mattern function or some other functions of interest, no problem. So then we estimate, based on the data, we estimate this sort of parameters, which are the so-called hyperparameters. So what the importance is, at the given data points, the GP model will just tell exactly the same value. So if we just use glider to make measurements and use it, it will just exactly show that. The GP model will exactly show. So that point, the covariance information will be just 0, but all other points, there will be a bit of uncertainty associated with it. So that's quite good. So what we do, we just use that model to predict at a later point. So this X star is sort of like a test point based on the sort of available data. Well, this is we could say this as machine learning as well in some sense, but I am reluctant to call. But many people are now calling this as all machine learning and AI. But this is more in Bayesian optimization idea. So predictive variance, because at a test point, at a future instant or at a different point where we want to do test, this is the sort of associated variance and associated mean. We know based on this, we can just plan our path. And the flexibility is of the Gaussian process model is the sort of covariance information as well. So we can make use of either just a predictive mean alone or a entropy as well information. So this is where how we tweak to have the information gain. Whether we want to do an exploitation, we just limit only with predictive mean. But if we wanted to have a little bit more exploration of the area, what we do is we do entropy as well. So we combine these two information. And so just an example how we do this is the sort of data, sea surface temperature data. And this is the form θ1, θ2, etc. So this data set, we pick A and B two set points at a distance along the friend about 130 and about 400. This is how the data will look like. And we obtain the sort of GP model for θ1, θ2, θ3, θ4, these sort of parameters of the function, and use that to just obtain a very smooth data. So it's basically like a function approximation. That's let's put it that way. And but the key point is it's just above the function approximation because it also gives us the uncertainty information, the covariance information that can be used very effectively. I'm just speeding up a little bit because I'm seeing the time is 55 minutes. So this is the sort of showing how the sort of information we made use from different agencies to come up with a probabilistic model. So we wrote the code for the GP to make the prediction of this sort of about 10 square kilometer of area for about 6 days ahead, using the sort of data from the PML. So they have this ERSM model, which just tell about the sort of how the chlorophyll will just evolve over time and date. And then the Metaphys data, which also tell us about how statistical forecast based on the sort of satellite information and everything. So 1 per day we obtain that, and the glider measurements we obtain. So all this data we make use and create a probabilistic GP model to forecast. So for inferencing, we make use of both like a nested Laplacian approximation as well as sort of variational inference method. So which give us every sort of 6 hours, every hour we can say what will happen on that specific region. And a timestamp is shown here, how the chlorophyll look like and where the maximum occurs, etc. So then we make use of a lattice graph of various reachable points, introducing from a point of deployment. And these blue lines are sort of with the maximum velocity for the glider, which is reachable in 1 hour, because we don't want to surface the vehicle all the time. So we want to have an idea where where it will reach. So the sort of this one will reach, at least if you pick in 1 hour, it is like a circle. But for doing the optimization very quickly, we just consider sort of lattice to begin with. You could have more spokes here and introduce more honeycomb structure or etc. But this one itself was sufficient, and yeah, itself creating complexity as well, because we wanted to start with something simple and develop further. And about 24 hours, we look ahead, and we considered all these mooring locations, risk maps, no-go regions, will just come as sort of taking out some of the sort of nodes of the graph. And then also the bathymetric constraints checks in place. So we don't, at the bottom bathymetry, we don't totally look, we just check once we get it. We haven't accounted it because, yeah, total information on the shelf C wasn't available. So the sort of idea is, if we, over that region, we put a graph, the idea is to get a path connecting 6 nodes, because each edge is of 1 hour. So each edge is of 1 hour duration. So we want about 6 hours path we want. So 6 nodes need to be identified such that the path connecting these 6 nodes, the weight, this weight is basically the sort of path integral of the predictive mean. So like the sort of information gain, or it could be just the entropy included as well. So we are trying to maximize that path integral. And in continuous time, it is sort of like integral, but in the discretized version, it will be the sum. And this we make use here the value from the GP model to do so, because each edge will assign a weight based on the sort of surrogate. And we do this. So this is the sort of framework, how it looks like. At Etc, we do collect all the data from the website automatically, every one per day, and all that frequency matching, and we come up with a Gaussian process model for that specific region. And determining that model takes about 60 minutes, about 1 hour for the region. And then based on that, we create a path plan. And this path plan, as we discussed, using the graph idea, it will take only 5 minutes. So that's very fast. And okay, all these calculations are on a GPU. And as an outcome, we send this through an email. Once this is all done, we send this as an email to NOC. This is how it is showing the sort of lat-long informations in the JSON format sent to NOC to do the commanding. And so it is interlinked through the C2. So just quickly a video of so that's where we deployed. Just on the way, it's just the deployment is shown. So that's the Eddystone around there. So we go there to deploy. So that's the Slocum glider, NOC owned one. So it's unfortunate that because of the COVID, we weren't allowed to get on board on the ship. Otherwise, not on the ship. Otherwise, we could have just visited there as well. So this is how they deploy. Very simple. Just put it in the water. But it's nice to witness. And so these are buoyancy driven, and these are the sort of points when it surfaces, it send information to satellite. And there is a thruster as well here, because they were worried here. They added the thruster because they were worried that it may get stuck in some sort of a muddy region or so. They wanted additional power. So that's in water, and we start commanding it through. We haven't got more longer videos, but yeah, it just come up. That's the sort of buoyancy driven, and once it receives, it start diving. So yeah, I think that's there. And just to say what happens is we also monitor all the surfacing positions. So this is what the red lines are, the sort of fence. So these are this is the sort of regions where all our sampling should confine in this region here. So in this region, so we always monitor the GPS surfacing positions in that week. So on 14th June, so yeah, we spilled over a bit more time for the testing. So 24 hours, these were the region which they were surfacing. And this is just to show how the optimization work. So the top one shows us this top diagram shows the region lat long and at a surface level how the chlorophyll concentration look like, not at surface level, sorry, at 5-meter depth level. So that's considered as a surface plane. And this is between the sort of 0 is the surface above the sea. This is the 5-meter and up to -50 below, so the depth. So this yellow shows the larger chlorophyll concentration. And so the idea is we need to move in forward in time for future horizon wherever this yellow color goes on. It's an early made video. There is some drawbacks there which we needed to work out to bring out the quality. So it's okay quality, but it can be improved. So it's just on the XY plane and it shows wherever the change happens. The red color is just it showing the times it just dive, and you can see in between the surfacing there are multiple dives, and yeah, and it just locate in depth the specific region where this yellow color is maximum, and there is more density there as well. So yeah, it requires more analysis of the result to present nicely, but yeah. And we also estimate because I mentioned the dead reckoning, we also use the sort of concept to estimate the glider speed. I'm done with, I just 3 more slides, so 5 more minutes only I will take maximum. So sorry for running a bit late. So yeah, this is the sort of estimate. The speed is slightly different because sort of all the oceanic drifts and waves will affect. So we haven't done any Lagrangian correction because the data set which Metoffice and etc. provides itself constitute for all the sort of Lagrangian correction. So we didn't do. We did say we have method to do that, but the suggestion at NOC was let's not do overcorrection there. Let it go like that. So next time we will do a bit more of that testing as well. So what the next? So that's the sort of end of the glider trial. There are more results. I don't have them all ready yet because it's need to be validated by all the groups and everyone. So there is things are going slow as well. So yeah, we haven't published anything on this yet. So it's all just so yeah. And this is a reason I haven't just gone too detail about the optimization stuff and all the sort of details as well. Hope you understand that. And where we do next, what we do next immediately is the plan with cooperative samplings idea. So where we are going to do 2 vehicles. So this is the sort of Medusa which technical the Portugal Lisbon people has. So the group with Antonio Pascual, we have a grant which we should have done together in the COVID time, but we kept back that. We have now resource. Possibly we will plan it soon before the next waves appear. So the idea is 1 vehicle, a slow vehicle, tightly track the contour. This is the sort of a dynamical scenario based on the data set which we did for 2 vehicles. And the red one is a bit faster one. So like it can just oscillate. So they are just having a leader follower, but the follower just oscillate in between. It's the sort of idea to gather more information and around that. So the oscillation we can adjust as well. So that's the sort of idea. And what other things we are planning to? So we need to develop more interoperable methods and tools. Yeah, there is a lot of theory. We can just do many numerical examples and etc. But actually, to take it into the sea and to get things in working, it's a lot of effort. So we need to develop more tools which can handle multiple platforms, multiple sensors without much difficulty. So then teaming of the heterogeneous assets and sharing the information. The sharing information, there are a lot of theory again, but how in specific applications we can make use of the surrounding specific assets, mooring devices, buoys, etc. How that can be used for localization, and there are a lot of work to be done there as well. Then it's critical to develop a integrated taxonomy linking all the sort of legal, because now, as shown in this nice cartoon, it's going to be heavily populated by all this sort of autonomous devices and on top of it, autonomous shipping as well. So we need to link it with the legality aspects and regulatory aspects with also ethical aspects, because I do these things, but I am sort of against many things to be explored as well, because it also creates trouble for many other animals and everything. So basically, I believe we should have limited autonomy and everything, but I'm doing a conflict, so sort of confused mind when I think about the sort of aspects. So there should be some level of autonomy in the. So how this sort of integrated taxonomy can play at the design time itself, and it gives us different scenarios. So we are putting a proposal and work on that, which I expect to finish in August. Then the autonomy should support all the sustainable and zero carbon emission ideas. So making the vehicles more glider in that way is nice, because they are buoyancy driven and very quiet. So it's not creating much trouble. But when we do start networking, it will create all mess. So we need to think about it further. And so those are some sort of thoughts I have. But then operation and maintenance. So next, another project I have now is a European Regional Development Fund for offshore floating offshore wind platforms. So we are going to try how the autonomous systems can be used to do the operation and maintenance of it. Again, periodical sort of things like what we are looking here, information enabled aspects of it. So that's me. Thank you all. And sorry, I have taken another 6-7 minutes than I originally intended. Sorry about that.
Thanks, Pratyush. So it was pleasure listening to you, and especially the first part, seeing the sliding mode control implemented for braking, and second, apart from this probabilistic framework we use for filtering, but I think I have not seen the practical work where it has been implemented for planning, and especially this covariance. Covariance in the planning, where you uncertainty, how you deal it. So thank you very much. And 2 questions. So I don't know how would you like to go, Professor Datta?
Yeah. So maybe we have time for maybe 2 or 3 questions at most. So yeah, Pratyush, you can see the question on the screen. I think in the right side menu, question answer. Can you see it?
Oh, okay. So maybe I end the slideshow.
Yeah.
Yes, you can do.
Okay. Is it?
You open the browser in which this video thing is happening, the portal.
Yeah, there is
right
a general question. Okay.
Q&A, yes.
So Amir Hayat asking, what are the suite of sensors used for navigation? What is the built of the GPS used and its accuracy for underwater and up to what depth. So I have not just used any. So that's what I was saying. I have not selected the sensors there. What we are doing is we are working with third-party vehicles. So they come with that specific configuration. So each of these vehicles, they have their own. It's nothing different. It is just Teledyne Slocum glider. That's what it is. The other one, so which I don't know its price. I know the price of EcoSub. EcoSub for 500 up to 250 meter depth, it's about 12,000 K, which comes with a specific configuration, and we make use of that. We are not looking at other details there. That's what I was saying. My interest is more at just at the guidance level and putting these sort of algorithms work. And of course, theory, we can have all assumptions. Everything is accessible and different ones. So hope that answers. I don't have the details of my other than the technical specification of the vehicles I can share with you. But it is accessible on web. Just if you search Teledyne EcoSub electric glider, you will see them. What marine ecological changes has been identified considering global warming and the predictions of timeline for an alarming situation based on the data obtained? Well, there is always this say of the tipping point is near. I don't have an immediate answer to that question, but what we have seen is there is a drift in the pattern which happens. So in terms of when the algae bloom occurs, there is a drift. This is widely, I think you are also seeing there, because when the monsoon starts, the time it doesn't start now, it's just spread all over in India as well. So but there are issues there. I don't have answers. So for the number, how many, how soon, etc. So again, sorry. This is a bit of disclaimer I made. I'm not really an ocean. Sort of, I should have made a disclaimer that I don't know anything. Perhaps now. Sorry. Ranjan Dasgupta. Is it the sonar sensor only being used for underwater localization, or IR laser may work as well for sonar sensor for underwater localization? So for the gliders, we don't do the sort of, we just say this is the whole issue here, because for the gliders, you just set the waypoints and it just you expect that it will pop up there. But it may pop up. In many cases, it popped up somewhere else, totally different, because of various drifts, and there was in between storm and everything. And we have no idea as well, because it follows the dead reckoning, and we don't do any localization there. There are some efforts started with keeping some sort of device, this sort of devices on the buoys around, and just restrict the region of operation, because what we are doing is far out in the sea. It's near the, like I showed you in the map. It's far out in the sea, and there are no real other equipments kept there. But there are ways, and this is in discussion, how we can make use of the sort of sonar and these devices, and underwater the sort of modems, so sonar modems and etc., to just try to figure out where exactly. But again, the problem, that's what I was just in one word I was mentioning, that as interoperability, because yeah, you can come with a device and say this is all working fine, but when we want to do actual mission, it doesn't. My experience is it's not easy. Say for example, we put a depth sensor on the vehicle, and it took about 7 months to get that, just the depth sensor purchased commercially off the shelf. It took 7 months to put on that vehicle because these are configured vehicle, registered vehicles, regulations, etc., everything. So there are limitations there for me to do much. I don't get it. So Ranjan has one more question. System calculates waypoints from GPR model. Yeah, but how paths are being planned waypoints? Yeah, it's by optimization. Yeah, you could use RR. You can start with RRT, yes, but we have done slightly different. I haven't gone into that detail because we haven't yet published. But what the idea is to find a path which has the edge weights maximum. And there are different possibilities to do that. You can do just you can try RRT, no problem. Then there are some other algorithms as well. Then you could do Monte Carlo, you can do graph certain optimizations, etc. So, but we tweaked that algorithm, and we are now working on its complexity proof. So it's a bit. That's why I didn't just share it, because we haven't just communicated it to put on that. But yeah, it's making use of the graph theory, and sort of there are sort of ideas about the connectivity and how well connected and how you maximize certain eigenvalues. This sort of ideas can be made. But the idea is basically like it's a again, we can make it very complicated, but here we considered very simple lattice because of the practical implementation purpose. And that lattice is you need to think of as like it just keep changing as well. So like the start point and so sort of there is a game. You used to have it in long time back, the sort of snake or something, like you just or it's like that. It keep moving, and the edge weights also just dynamically change, and we need to do the corrections accordingly. So it's that's all I would say, Ranjan, on that. So Ranjan, is any disturbance observer-based focus control being used along with the SMC to navigate underwater drags or we have done in theory, but no, none of them, because they don't want to do tight control. And in oceanography applications, so when I just fell off the chair when he told, I told, oh, these waypoints and everything, it works fine. Like we wanted to get my probability radius about 10 meters for the waypoint to say achievement and all. He just laughed and told, put it into 100 meters. And it is true, because you never get that close in reality. So it's in a confined environment with created disturbance and all, yeah, you could show that tight and all. These are again not requiring that level of tightness. But there are applications I have not mentioned them, which link to sort of defense. There are applications where things need to be tight. And one key issue here is if you are putting disturbance observer, how will you put it on this third-party vehicle? Or you have to build everything. Otherwise, you have to work with Teledyne to do this reality. And theory we can do, no problem. I have done, and this sort of works on disturbance observer for basically for it's a quadcopter type dynamics. What you do for the disturbance observer using sliding mode, it will work fine. We have done some tests with people. I have a project with IASC, and now he used to be in IIIT Delhi. He is now in somewhere else, Sujit, and Debashish at IASC. So we have some work in this line of disturbance observer for unmanned systems, and we have done some flight tests.
Aisar Bhopal.
Eh?
Aisar Bhopal is.
Yeah, I said Bhopal. So I got a bit. I couldn't remember the Bhopal,
Yeah.
and I was sure it was in Pune, so I didn't want to say wrong. So earlier he used to. So yeah, we did that. So some similar sort of things are possible to do the drive. So I
Yeah, I
believe,
think-
Ranjan, I answered that. The last question is Venkatrangan MJ. Do you use mission planners like normally drone for drones? I missed your any specific simulators for. No, it's the mission. It's done slightly differently here because we work with the command C2 at NOC. They have their own. So it is like the NIO Goa. They have a specific set of plans to do this sort of thing. So whatever you do here, the reason why I do this way is also related to here, at least the research. If we want, so sort of like a fashion or like how the project money driven. So to receive the projects, you should have impact. Theory papers and everything we can do at our leisure time on Saturday, Sunday, but to get the project, we need to have real impact. The impact comes with integrating your research in a existing system. So that's what also called the enhancing the technology readiness. Hello?
Yes, we can hear you, sir.
Okay. Because all of a sudden I saw some changes on my screen. So that's all. So yeah, that's what. But for drones, yes, there are. So Ardu Pilot and all those sort of things are there. So yeah, you can use them for mission planning. So I hope I answered you, Venkatrangan, the question.
Okay. Professor Ashish Datta, are you there? Both of them went. Maybe IIT Kanpur probably has internet blackout for some time. Let's wait for some more time,
Yeah, no problem.
because usually if both people go at the same time, that could be one reason.
Okay. No, I saw all of a sudden here my screen just.
Yeah, both disappeared from the list also.
Yeah.
Okay, I think they'll just join back.
Okay, no problem. I can wait, and there is something in chat, and
Yeah, if there are any further questions, kindly type in Q&A. So followed by this, the participants are informed that we have a very short valedictory function and the closing ceremony. So kindly stay back. We also have a small slideshow, which I thought should be a surprise, but nevertheless, if people go out, we'll not have any surprise. So just please stay back. We have made one small slideshow of some of the images we had captured during the conference. Okay, Professor Ashish Datta is here.
Yeah, sorry, I got cut out. There was a sudden spike. I don't know from where, and it cut me out. Okay, so thank you, Pratyush, for sparing your time. It was a wonderful
thanks,
presentation.
Professor Ashish.
Yes, fantastic, with a lot of theory and practical experience. So so I hope everybody has enjoyed the talk. And you can get in touch with Professor Pratyush Menon for further questions. I think I see some more questions, but I think I'm sorry that today there is no more time. So what we'll do is we'll move on to the last part, that is the closing of the conference. So yeah, so I think Professor Ashokan, are you there? Is he there?
He was here. I'll just ask him to join back again.
Yeah. So we had 4 days of conference. We started off with the India-Japan workshop, and then 3 days of paper presentation and conferences. So towards the end, I would like to thank all the authors, okay, who are here and who submitted papers, all the reviewers, and finally the people who made their presentations. Okay, so for that it was this is a conference we hold once in 2 years in India, apart from IEEE and the other conferences. So we look forward to seeing you again after 2 years. It's not decided where, but it will be there somewhere. Okay, and I'd like to thank all the reviewers for reviewing papers, the authors for submitting, all the session chairs, plenary speakers. We had speakers from Japan, we had from Korea, we had from Europe, okay, then from UK. Europe is not a part of UK anymore, or the other way around. So if I say UK, if I say Europe, it's not enough.
Well, confusion then.
Yeah. So I'd like to thank all the speakers, plenary speakers, keynote speakers. I'd like to thank Rajiv, especially Rajiv Lochana, who was there. He's the one who managed the virtual world. Okay. So we are all meeting in IIT Kanpur, but virtually. And he's the one who managed the virtual world. And I'm also surprised that we were able to have 4 days of continuous workshop without any interruptions. We managed to have paper presentations, talks, and we were really scared. We were really scared in the beginning whether it will work out, but it did work out. And today afternoon, actually, I had kept about 1 hour free, that all the people who will miss their papers because of whatever reason, they can come today afternoon and present. But nobody missed any paper, so we were early in the afternoon today.
Okay.
And yeah.
Later. So it's a bit later, sorry.
And yeah, so I think Mangal has been cut out also.
He joined back.
Yeah, he has joined back.
Yes.
Professor Ashokan is there?
I tried calling. He is not taking.
Okay. Yeah, so Mangal is also there.
Sorry, so we have a power cut.
No problem, no problem.
Got disconnected.
So yeah, so from the participants, if anybody would like to have any feedback or your views, how we can improve, any issues that you faced, please raise your hand so that we can bring you on stage and then you can express your views. Is there anybody who wants to say anything?
There is a raise button somewhere, raise hand button. We don't see it.
How
Yeah,
would we know who?
Navneet has raised. Yeah, we'll keep making them as speakers. Amir had raised. Okay, Rajshekhar. So we are just adding one by one. If you're not added, please, we'll add you. Don't worry.
Okay, Navneet MG is there. Yeah, so you'd like to share any feedback and views on the conference and workshop?
Yes, sir. Actually, starting from the first day, the Indo-Japan workshop, it was really captivating. It was an eye-opener for me. I got to introduce to a lot of information. And also in the afternoon session, the MATLAB session on reinforcement learning, that was really helpful for me. And after that, all the sessions, all the papers, they were grouped so accurately, and all of them were engaging. And the plenary talks, I was able to attend almost all of them. It was a really great experience for me. And I would like to thank Ashish Datta sir, Rajiv Lochana sir, then Ashokan sir, Saha sir, everyone, to organize this program in such a wonderful way. There was no difficulty at all. The link was always accessible. So it was a great experience. So, and I hope in the 2023 we will be able to meet in person. Thank you, sir.
Yeah. Thank you. Thank you. Yeah. Next is Rajashekar.
Yeah, I'm Rajshekar. So this conference was very helpful. We came to know about a lot of people who do research in a particular field in India, and networking was the toughest task which I felt when it was announced online. But the networking platform was really good. We were able to share our screens and express a lot of thoughts and exchange views. So networking in that aspect, this online platform was the best when compared to others. Even if you have met in person, this net kind of networking by sharing screens would not have happened, because we have all things with us. We can even show the prototypes and discuss. So this kind of thing, networking is good. That's it from my side. Yeah.
Okay. Thank you, Mr. Vilas.
Yes, sir. It was a great experience. I was very surprised how you people have managed this kind of virtual workshop, virtual conference. Uh, I felt one regret, not able to follow the not able to paper, but then also I have participated in most of the sessions. I've missed few, but it was a great experience, especially Ashish Datta sir, Kotari sir, and Raju Lochana sir has perfectly managed my third consecutive conference, and even from physically, this was more better, I can say. Thank you for such a wonderful experience. Thank you.
Okay, thank you. Anybody else?
Amir had joined. I think he has issues with his webcam. Amir, maybe you can
Okay.
try.
Hi, good evening, all the attendees and the professors. Can you hear me?
Yes.
Yeah.
Yeah. So good evening, all. This year, witnessing right from the beginning of the conference since 2013, then 15, 17, and this year I could not submit the paper, but I just followed almost all the key sessions and paper presentation. And this portal is quite nice to observe, because say in other conferences like ASME, IDTC or ICRA, they or the recorded videos, which is doesn't give that feeling of interaction. But in this, like live to live, getting the questions and presenting live is also nice. And all the sessions were very nicely organized. With this, yeah, I'd like to congratulate all the team and thank you for even letting the people who are actually not registered for it. So actually, I was not registered, but I could attend this session as well. So thank you so much.
Okay. Thank you. Anybody else, Rajiv?
No, sir. I don't see anyone.
Okay.
If people want to raise their hand, kindly raise your hand. We'll add you on stage. And those who have spoken will just make them move out.
Okay. I think that is all right.
Yeah, I have the slideshow. Whenever you are
Yeah.
ready,
So you have taken the pictures at every session. Slideshow of that, right?
yes.
Yes. So yeah, some information or rather announcement. One is at the beginning of every session with all the speakers, we have taken screenshots with all the speakers on stage. So that will be putting up in the AIR website. Okay, and Rajiv is also going to show it here. So you can download your pictures, okay, from the website. That's one. The second is that we have 2 awards. One award is for the best paper award, and the second award is sponsored by the Japanese Robotics Society on a best paper in the area of humanitarian robotics. So unfortunately, I have not been able to compute or calculate all the marks and arrive at a decision because I was too busy. Unlike a conference where you can start the session and walk around, I had to sit here on this chair for the last 4 days. So I couldn't do that. But I hope next week we'll be able to announce these 2 awards. Okay, so we'll put it up on our website. These 2 awards would be announced on our website. Okay. Apart from that, we hope to see you in the next conference. 2013, wherever it is, in person, hopefully. Okay. And please, we do have a Robotic Society of India. Okay, on the website, you can go to Robotic Society of India. We organize regular talks, webinars, talks, industry events. Then the Robotic Society of India has student chapters. Okay, various institutes have student chapters. So those of you in various institutes, if you want to start a student chapter, you can get in touch with Professor Ashokan of IIT Madras, who is the secretary of the Robotics Society. Okay, so the whole idea is that robotics is picking up in India. Okay, we are a little late compared to other parts of the world, but we are picking up, and we need to network amongst ourselves to know who is doing what and how we can help each other. Okay, that's the whole idea of the Robotics Society. Okay, it was started 10 years ago, so we have just completed 10 years, and we have held 5 conferences. So with this, I think we'd like to end. Okay, we hope to see you again in the next conference, 2023. Okay, okay, bye-bye, and see you.
Thank you.
Thanks, thanks, Pratyush, very much.
Thanks, Mangal, and thanks, Professor Ashish. Thanks.
Thank you.
Okay,
Thank you.
okay, bye. Thanks all.
Bye. Yeah.
Yeah.
Okay, there are a few messages. Probably I'll just read out. Atul Thakur, Dr. Atul Thakur says, great conference, sharing of ideas by eminent speakers and updates from various research groups was a enriching experience. Congratulations to Professor Datta and entire team of AIR for meticulous work and successful conference. Thank you. Anubhav Dogra, really enjoyed this conference in online mode, very well managed and conducted. Glad to be part of this conference since 2017. Well, thank you. We are also glad to be part of this conference since 2013. Yes, sir.
Yeah. 2013.
13. Yeah.
Yes. 13. Okay. Yeah, I think that is all then. So what we have to do now is these 2 paper awards. By next week, I'll figure it out, and then maybe I'll discuss with Ashokan also once, and then we can put it up on our website.
Sure.
Okay. And
the videos of the sessions, I think, are getting recorded in your YouTube account. Your
okay.
Ashish Datta YouTube account.
Yeah. Yeah.
So we'll once like today's recording will also come by tomorrow. It's getting some time for processing. So we'll put those videos also on website.
Okay, we can do
the
that.
Links
also,
to the videos.
Yeah, right from the first day to the last day. That will be a lot of data, I guess. But I don't know. Let us
2 hours
yeah.
video they have made in YouTube, and we'll also try to get the information from the town script. We'll see what they give. Accordingly, we'll put it on our website.
Yeah, I think the town script one may be better because YouTube, what it is doing, it is capturing the screen. I was having a look. So it is not coming on the presentation mode.
Yes, it will show 3-4 people, then all will come.
Yeah, exactly.
Maybe
what we are seeing now, it is showing that only.
Okay.
So maybe we can see which is better and put it up there.
Sure, sir.
Okay.
Okay, sir. We'll close this and we'll go to the tables, and all the participants, you are free to walk around till 6:30. You can interact with all other colleagues, attendees, and the portal will close at 6:30.
Yeah. Okay, I think we can go out, right?
Yes, sir.